Super important concept today. We're talking about summer design conditions. The difference between your summer peak dry bulb condition and your peak enthalpy condition. Or you can think of it as, should I design for the hottest day in the summer, or should I design for the wettest day in the summer and include the humidity values in that assessment? I'm going to explain how to analyze this and how it affects your coil sizing, especially for DOAS units that are going to bring in 100% fresh outdoor air. Let's take a look. To demonstrate this, we're going to look at a couple different outdoor air conditions and assess the impact on a coil. So the first condition we're going to look at is the peak dry bulb condition. And when you look up your design day, you're looking up your ASHRAE weather data, you're going to see the peak summer design condition likely coincides with the peak dry bulb condition. So in this case, we have 100 degrees Fahrenheit dry bulb, and the coincident wet bulb temperature at 100 degrees, our peak dry bulb, is around 72 degrees wet bulb, or it's roughly 25% relative humidity. So these could be the numbers that you get when looking at your peak summer condition. This is the hottest it's going to get. You can design for that. Before I get any further, let's visualize what's actually happening at this unit and what we're trying to accomplish. For this example, we're looking at a DOAS unit. It is most impactful when you have a situation where 100% of the air is coming from outside. So the conditions I just showed you, that's 100 degree Fahrenheit dry bulb air, roughly 72 degrees wet bulb, that's coming into this unit. And let's say we need to condition 3000 CFM of this air, and we're trying to deliver 55 degree Fahrenheit air to our spaces. So this coil needs to take 3000 CFM at this condition and bring it down to 55. What is the load on the coil? The load on the coil is represented by this path here. The coil is going to cool this air sensibly until it reaches the dew point, after which you're going to extract moisture until you hit the desired 55 degree set point. And we can calculate this load in terms of BTUs. I'm going to calculate both the sensible load and the total load so I can show you the difference between this peak dry bulb condition and our next condition. The simplified equation for a sensible load is equal to 1.1 times our CFM times delta T. This is going to yield 148,500 BTUs. We can also calculate the total load with the information that we have here. The total load equation, simplified, is equal to 4.5 times your CFM times your delta H. We can find our enthalpies on the cycle chart here. So for state 1, our outdoor air, I'm going to follow this line up to the enthalpy, and we're looking at about 35. For state 2, I'm going to follow this line up as well, and that's going to be at about 23. So now I can complete this equation, 4.5 times 3,000 times difference between 35 and 23, which gives me 162,000 BTUs. This is our total load on the coil in scenario number 1. Let's look at scenario number 2. Here, the outdoor air is at peak enthalpy conditions, and you'll notice that the dry bulb is only 90 degrees Fahrenheit, but the wet bulb is up at 75 degrees, or 50% relative humidity. It's not your hottest day in the summer, but there's additional humidity. The DOAS unit in our last scenario now has a process curve that looks like this. It's going to cool the outdoor air sensibly until it reaches the dew point, and now there's much more moisture that needs to be extracted to get to a 55 degree leaving condition. Let's run the numbers on this load. Your sensible is 1.1 times 3,000, except this time it's 90 degrees minus your 55, and this yields 115,500 BTUs. Sensible. Our total load, 4.5 times 3,000, except this time the enthalpy for state 1 is right around 39. State 2 is still about 23, so we're using 39 minus 23. Our total load on the coil in this scenario becomes 216,000 BTUs. This is a higher overall load on the coil than scenario 1. So let's break it down. Scenario 1 was peak dry bulb, 100 degrees Fahrenheit, the hottest day we're going to see. The sensible came out to 148,500. The total was just 162,000 because there's very little latent load. Scenario 2 is our peak enthalpy day. It's not as hot as a 100 degree day. It's 90 degrees, but it's more humid, 50% relative humidity. The sensible load is lower than our peak dry bulb. However, because of that extra humidity, our latent load is higher, and the total load on the coil ends up being 216,000 BTUs. So if we're designing a DOAS unit, we do not want to design it for this day. We want to check this day. When is the peak enthalpy, the peak load that this thing is going to see? And it comes out to this number here on a day that might not be the hottest, but you have that extra latent load. So what's the best way to run this assessment for your project, aside from doing all of these psychrometric chart hand calcs that I just showed you? With HVAKR, we actually make this really easy to assess on the fly. So right here, I have an example project, and this is based on default ASHRAE weather data, my summer design conditions at 0.4%. I have a dry bulb of 97, a coincident wet bulb of 68. My total load for my system here, just looking at my coil data, is 19.2 tons. Great. But what if I want to check a different outdoor air condition? I can look at what the monthly design data is here, and I'll see, based on this weather data, this station actually peaks around 97 in September, but the wet bulb peaks earlier in July, around 72. So if I wanted to check different conditions, I could check, all right, peak wet bulb coincides with 93 dry bulb, and I can enter that in. So So 93 dry bulb, 72 wet bulb, and I can see in real time this data update. So I was at 19.5 tons, but with more humid conditions, the peak wet bulb day, I'm actually at 21 tons. So this is telling me the ventilation air I'm bringing in is actually driving this unit up when I'm accounting for a higher wet bulb condition. If I want to stick with my original because humidity is not a big deal, it's okay if it fluctuates a little bit in the space, I can revert back and I can instantly see what the original was, 19.2. So this is a quick way to do that assessment without having to go through all the hand calcs that I just showed you.